Hello. Today we are going to derive Hamilton's equations of motion. So the Lagrangian is some general function of the coordinates and velocities. So in other words, we can write the Lagrangian L as being a function, of the generalized coordinates. So Q for position, and we have Q dot for our velocity, So this is a generalized coordinate system shown by Q. So the Hamiltonian is written as this. We have H equaling the sum of I, which is just the number of dimensions or variables you happen to be dealing with, of Pi multiplied by Q dot I, minus your Lagrangian. So we derived this in the first exercise of classical mechanics. So if you haven't seen that already, then you might want to check it out if you're unfamiliar with this. So the Hamilton's equations look at change. So in order to derive them, it makes sense to work out the change in the Hamiltonian. So the change in the Hamiltonian, using our definition above, is simply going to be our normal sum of I, of Pi times the change Q dot I, and then we add Q dot I times delta Pi, like so, and then we minus the change in the Lagrangian, just using the definition we have up here. Alright, so now what we can do is work out the change in the Lagrangian. So this is going to equal the sum of I, exactly what we have here, so Pi delta Q dot I, then we add Q dot I times delta Pi, and then from that we minus the change in the Lagrangian, which you should already know is simply going to be the partial derivative of L with respect to Qi times the change in Qi, and then we minus, because it's minus delta L, so we're going to do minus the partial of L with respect to its velocity component, Q dot I, times the change in your velocity, like so. Alright. So, now if we use the definition of momentum, namely that Pi, just using our Euler-Lagrange equation, we should know that it's dl by dq dot I, So using this, the first and last terms you can see is cancelled because Pi and minus dl by dq dot I will cancel because Pi is equal to dl by dq dot I. So therefore we can simplify this expression up here, and we get the Hamiltonian is simply equal to the sum of I of Q dot I times the change in Pi, and we minus dl by dqi times the change in qi, like so, Why? Because Pi and dl by dq dot I cancel, and our delta q dot I will cancel with our delta q dot I on the other side. Alright, so let's bracket that off like so. Right, so let's compare this, what we have here, with the general rule for a small change in a function of several variables. So this should be quite familiar. So the change in H, we could write this as its components. So we have Q and P. This is in phase space. This is going to equal the sum of I of dH by dPi, times the change in our Pi. And then to that, we simply add the partial of H with respect to Qi. times the change in qi. Okay, that's the general change of a function h of several variables. In this case we have q and p, so therefore h is our Hamiltonian. So now, by matching the terms proportional to delta qi and delta pi, okay, we can get the Hamiltonian equations. So we have delta pi here, and we have delta qi and delta qi. Okay, so this is very, very similar. So therefore, they should be equal. If we match dh by dpi, which we have here, with q dot I, okay, and then we match minus dl by dqi with dh by dqi here, we can derive the Hamilton equations. And so therefore, dh by dpi, the partial of h with respect to pi is equal to q dot I. That is our first Hamilton equation. And the second one, what is it? So it's dh by dqi. So we have dh by dqi okay, this is going to equal the negative partial derivative of L with respect to qi. So minus dl by dqi. Okay, and of course from our Euler-Lagrange equations, you should be able to see that this is simply the time derivative of our momentum. Okay, so you can rewrite dh by dqi as simply being negative p dot I. Okay, and so this is our first Hamilton equation, and this is our second Hamilton equation. Okay, so there's a nice simple derivation of our two Hamilton equations, simply by computing the change in the Hamiltonian. So in the next video, we'll be looking at Hamilton's equations in a bit more detail and looking at the application in physics. So I'll see you in the next video.